How does decoherence create classical reality? Imagine a tiny particle that can be into places at once or spin into directions simultaneously. That's the strange world of quantum physics, where particles behave very differently from the objects we see every day. But somehow, this weirdness disappears when we look around and see a solid, predictable universe. So, how does that happen? The answer lies in a process called decoherence. Decoherence explains how the fuzzy, supercharged quantum world turns into the clear, stable reality we experience. At the quantum level, particles can exist in superpositions, meaning they can be in many states at once. This is possible because of quantum coherence, which allows particles to interfere with themselves, creating strange patterns. Think of it like waves overlapping in a pond, creating ripples that combine in complex ways. But when a quantum system interacts with its environment, like air molecules, photons, or even tiny vibrations, something interesting occurs. The system becomes entangled with its surroundings. This means the quantum information of the particle spreads out into the environment, making the superpositions impossible to observe directly. It's like the environment is constantly watching the particle, causing its quantum state to become blurred. This interaction causes the off-diagonal elements in the mathematical description of the system, called the density matrix, to decay rapidly. When these elements disappear, the quantum interference effects vanish. Without interference, the particle no longer appears to be in many states at once. Instead, it looks like it is in one definite state, just like a coin landing on heads or tails. This process happens incredibly fast for large objects. That's why we never see a chair or a cat in a superposition. Their quantum states are constantly interacting with countless environmental particles, causing their quantum weirdness to collapse into a stable, classical form almost instantly. This is why the universe appears so normal and predictable, despite its underlying quantum nature. It's important to note that decoherence is not the same as the mysterious wave function collapse often talked about in quantum mechanics. Collapse is a sudden change that happens when we measure something. Decoherence, on the other hand, is a gradual, natural process that occurs all the time, even without anyone observing. It's like the universe's way of quietly erasing quantum fuzziness and making everything look solid and real. Scientists have even managed to slow down decoherence in experiments. By isolating quantum systems very carefully, they've observed superpositions in larger and larger objects. This shows that the boundary between quantum and classical isn't fixed. It depends on how much the system interacts with its environment. This understanding is crucial for developing quantum computers. Decoherence destroys the delicate quantum states that make these computers powerful. Researchers are working on ways to protect quantum information from decoherence, so we can harness the weirdness of quantum physics for future technology. So, in the end, decoherence acts like an invisible force that gently erases the quantum weirdness, leaving behind the familiar, stable world we see every day. It's the quiet process that transforms the strange into the normal, explaining why the universe looks so ordinary despite its underlying quantum oddities.